Saturday Morning Physics is sponsored by the Ambler Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
I'd like to talk today about symmetry. Excuse me. In particular, the mirror symmetry that you're all familiar with. You confront it every morning when you get up and look at that person in the mirror and think for a minute, why is his wedding ring on his right hand? See, when I face you here now, this is my right hand. The person facing you has this right hand, has the wedding ring on the left hand, right? The person in the mirror has the wedding ring on the right hand. The mirror reverses right and left. Seems like a trivial thing, standing in front of a mirror talking about it, but it has a deep connection with the fundamental physics of the world, and I'm going to talk about that today. Okay, the CDF detector, it's a physics experiment the size of a house. It's underground in Illinois. It sits, it's threaded through the center by the beam pipe of the Fermilab Tevatron. I'm going to elaborate on this more in a later part of the talk. This is just kind of an appetizer. Here's a schematic diagram of what happens. The proton and the antiproton, matter and its antimatter counterpart, approach each other at high energies and collide. In the collision, the matter and antimatter annihilate. Matter and antimatter are destroyed and converted into pure energy, which can then rematerialize as other kinds of particles. Some of the time, the other particles are a pair of top quarks, a heavy form of the fundamental quarks inside the proton. It appears only at high energies. They're fundamental particles, you know, there's not much about them you can measure. Think of them as small billiard balls, and this is a collision between small billiard balls. What do you measure about such a thing? You can measure the direction in which it goes. So we'll measure the angle. On the scale here, you see it's 0 in the center. There's positive numbers on the right, negative numbers on the left. A positive number here is measured for a top quark going forward. A negative number is measured for a top quark going backward. The green curve is the prediction from the standard model theory, which tells us that in the strong interaction, which is involved here, in the interaction between the initial quarks and the outgoing quarks, we expect a complete symmetry between forward and backward. The prediction given by the green curve is a completely symmetric distribution. The points are the measured data for 1,001 top events that we've accumulated over 7 years of running. 1,001 events, and we've measured all of their directions. And you see the data shows a slight tendency for the top quark to appear like it's going forward. The form of the data bump is offset from perfect symmetry at 0, right? An asymmetry between forward and backward. So here's the cue ball. Here's a colliding billiard ball experiment. We're going to collide cue balls and 8 balls. And in a collision like this, we would say the 8 ball is going forward and the cue ball is going backwards. in a collision like this, you would say the cue ball is going forward. You expect in a fair game of pool that in a set of collisions like this, that you would see this process with the same frequency with which you see this process, right? There is no fundamental preference in these collisions for the 8-ball to go forward or backward. This is a physical intuition that you have, right? You know, with our students, teaching students physics, to try to break them out of the rote of plugging numbers into formulas. We tell them when you confront a situation, use your physical intuition. Think about what you know will happen, right? And we all have a physical intuition here that there's a symmetry in this situation which tells us they should be the same. The symmetry is a mirror symmetry. Imagine if I put a mirror at the center here, represented by the sort of blue rectangle, and I reflect the outgoing billiard balls in the mirror, right? Here's one situation, and then I reflect the other situation in the mirror. In one situation, the cue ball, the 8-ball is going forward. In the other situation, the 8-ball is going backward, right? Your physical intuition tells you that if there's a mirror symmetry, there's really no difference, right? And therefore, seeing an 8-ball go out in this direction should occur at the same rate as an 8-ball going out in this direction. It's a mirror symmetry. Now, symmetry is a powerful organizing principle in our minds, in the way we perceive the world, in aesthetics, and in science. Oh my gosh. Can't be too careful these days. Right? Perhaps this principle is important in our minds because of the bilateral symmetry of the human body. We're all symmetric. Nature is full of examples. Nature is full of examples of symmetry. You know, like here, this beautiful symmetric snowflake. This is the diffraction pattern from the DNA helix. This diffraction pattern shows this beautiful symmetry. In fact, the X here that told Rosalind Franklin that the DNA molecule was a helix. This information then borrowed by Watson and Crick. Now, I'm talking here about simple pictures, but I want you to understand it's more than just some kind of thought exercise. You know, this is not like Aristotle or something just saying, well, symmetry is beautiful, therefore energy is conserved. This is a mathematical exercise. All right, so here's a picture of the two motions of the cue ball to the right and to the left. And in the mathematical exercise, in the description of physics with mathematics, mathematics is the text in which physics is written. Right? We describe this motion by giving this object coordinate x and a momentum p. Right? And then we can write the equation of motion or the wave function or any one of the physical descriptions of the object and describe the process. Now, if we reflect the process in a mirror, we reflect the process in a mirror, reflection amounts to the following mathematical transformation. Every place we see an x, we're going to put a minus x. And every place we see a momentum, we're going to put a minus momentum. Now, we can have some description of this process, equation of motion, And in that description, make this substitution for all the coordinates, and we find that the laws of physics stay exactly the same. Right? It's a kind of a conservation law. It doesn't have the same cachet as conserving energy or conserving momentum, but it is a conservation law nevertheless. And it's called the conservation of parity. Right? Parity meaning the equivalence of right and left. There's a parity between right and left. And the fact that the world, the fact that the laws of physics are the same if we reflect them in a mirror is called the conservation of parity. In lecture here, the escape that we provide for the students is gonzo demonstrations, you know, things flying through the air, explosions, and I don't have any good demonstration. I was ruining the fact, putting this talk together. What am I going to do to like keep people awake? You know, if only I could just do something like pull the tablecloth out from under a table setting. Then I thought, why not? You know, it's about inertia, kind of conservation of momentum. It kind of fits in with our theme here. I got to get a little warmed up first. Okay. Back to physics. Parity conservation. Now, as I've explained it here, it's a kind of a ideal principle. You substitute minus x for x in the equations, everything stays the same. It actually has a detailed and highly articulated connection with all kinds of observations and measurements in atomic and nuclear physics. The question came up in the 20s, I think, when it was observed that certain atomic energy levels in situations where you'd expect one state, there were actually two states with slightly different energy. And the great mathematical thinker Eugene Wigner realized that this was a case where there was a mirror symmetry, and there could be two kinds of states, one that was symmetric and one that was anti-symmetric in the mirror. And the anti-symmetric state always had slightly higher energy. See, nature prefers the symmetry. Right? Wigner, incidentally, he is the guy who brought the concept of symmetry to physics, introduced the idea of group theory into physics. In modern particle physics, our whole conception of the whole foundation, conceptual foundation, which understands the interactions as in terms of preserving certain symmetries, is due to this group theory principle that Wigner invented. So the conservation of parity, right, the fact that the world is invariant under the mirror reflection, right, is understood in terms of his formalism established with great precision in atomic physics, and then continued into the nuclear regime, looking at the alpha decays of radioactive nuclei. Here's a plot from my favorite book, Frauenfelder and Henley's work on subatomic physics. Frauenfelder did fundamental work on parity violation in the weak interaction, which I'll talk about in a couple of minutes. So this shows a radioactive thorium-228 nucleus, this energy level, decaying down to a radium nucleus, and in the emission of the alpha particle, this excited nuclear state decays down to these lower energy levels. The energy goes out as an alpha particle, and all of these energy levels are allowed. The plus and the minus here refers to a technical description of the parity of the state, and the numbers refer to the angular momentum of the state. So you see here that the state with spin 2 and positive parity is allowed. but there is no transition to the state 2 and negative parity because the arrangement of the quantum numbers here specifies that it must be of this parity. And tests like this show that parity is conserved at the, down to the level of 1 part in 10 to the 16th or something like that. It's established with great precision for electromagnetism in the atomic case and the nuclear or strong force in this case, right? That the world is invariant under a mirror reflection. Thinking of that in another way, if the world is invariant under a mirror reflection, it means when you look out at the world, you can't tell whether you're looking in a mirror or not. Okay? This stuff about mirrors, it's kind of abstract. I thought it might be fun to just stand in a mirror and talk about it more. What else do we know about mirrors? What is about our experience of looking in a mirror? Okay, there I am. Here's my left hand. There's his right hand. So the mirror reverses right and left. Why does a mirror reverse right and left and not up and down? Anyway, did you ever worry about that in the morning when you're getting ready? The reason is, the right and left is just a simple way of talking about it. What the mirror is really doing is reversing front and back, right? Because here's my front, here's my back, there's his front, right? And what the mirror has done is it's taken the back of my head and drawn it through my face, right? So that the back of my head is an equal distance from the front of my face on the other side. The mirror has reversed front and back. And in the process of reducing front and back, this sort of three-dimensional object, my hand, has the right version turned into the left version. Now, there's another way to think about this, another kind of familiar way that we think about mirrors that goes with right and left is, remember righty-tighty, lefty-loosey? Right? So our machine shop convention is that to tighten a screw, we turn it to the right. Right? It's a sense of a thread sense on a screw. Sense of a thread on a helix. Here's a left-handed helix. Well, the sense of the thread, what do we call it, righty-tighty? We call it a right-handed screw, right? You turn it to the right to screw it in, right? Here's a left-handed helix. I would have to turn this to my left to screw it in. Does everybody see that? Okay. We can relate this to our familiar right and left hands with a right and left hand rule. And it goes like this. You point your thumb in the direction of the motion, and the way your fingers curl around your thumb tells you the thread of the screw. So this is a left hand thread. The one in the mirror, oh, I see, okay. I don't know how well you can see that. Bear with me. The one in the mirror, you see, is a right hand thread. Because if I use my hand, this one, not that one, right? Here, the one in the mirror is screwing in this way, and it turns this way. So a right-hand thread has been turned into a left-hand thread by the mirror. Right? So this thread sense or twist sense is another familiar way of thinking about the mirror reflection. I just said earlier that if parity is conserved, if the world has a mirror symmetry, you can't tell whether you're looking in a mirror or not. Since a mirror reverses right and left, right? Another way to say this is you can't do an experiment to tell right from left. Now, there's a great way to think about this that I first heard long ago in my dorm room at MIT, laying in bed at night, talking to my roommate, Paul. And we're laying there in the dark. And you know, what do you do at MIT? What do you talk about laying in the dark at MIT? How do you tell right from left? Right? And so Paul said, well, imagine you are on the phone with an alien. You could talk, but you can't show them a picture or anything. Can't show them your wedding ring. Okay? And say that alien, we knew that that alien looked mostly like us. Kind of like that. How would you tell the alien which hand is their right hand? How do you tell them? You can't say your wedding ring is on your left hand because maybe in that society they don't have wedding rings. You can't tell them, oh, just go look at, you know, when you turn the screw to make the screw go in, it goes to the right, because maybe they don't have screws. What do you tell them? Is there a fundamental principle in the world that might be shared with someone on a distant star that could distinguish right from left? So I'm laying there in bed and I'm thinking, man, this guy is deep. You know? Right? And I went through my whole career in physics then. Whenever this topic came up, you know, I would mention this, right? And I was talking to one of my colleagues in the department last week about this talk, and I said, oh yeah, you know, I got this great analogy about this alien, you know, talking on the phone with the alien. And he said, oh yeah, like the Feynman lectures. And I realized all this time I'd been attributing this to my friend Paul, and he had not properly referenced the primary material. Now, in fact, nature is full of apparently incidental ways that distinguish right from left. You know, you pick up a conch, the seashell, it's got a spiral to it, right? If you knew that you know, they had the same seashells on the distant planet, you could use that. The original example that, you know, well, what are we talking about anyway? The difference between right and left hands. They're kind of similar, but you can't superpose one on the other. That's what makes them different. This property is called chirality. It has a name. A chiral object is one that cannot be superposed on its mirror image. You do mathematics for a while, eventually you'll learn all the Greek letters, you know? And so here's chi, epsilon, iota, rho. And chirality comes from this Greek word for hand, which must be pronounced something like chir. The world is full of chiral objects. There's all kinds of molecular species that are mirror images of each other, like these two imaginary molecules here. Mirror image molecules are called enantiomers. They are chiral copies of each other. You can't superpose one on the other, but because they're the same chemical species, they have exactly the same chemistry. You know, do a chemical reaction, these things will be used up or produced at exactly the same rate. It's kind of like the parity conservation, right? The world is not distinguishing between the right and the left version of these things in the fundamental sense, right? In biochemistry, the symmetry is totally broken. Right? In this example here, I show a generic amino acid. What makes an amino acid is this nitrate group hanging off of some other organic configuration called R. And there's right and left hand. Every amino acid comes in a right and left-handed configuration. Living things use only left-handed amino acids and only right-handed sugars. So somewhere back at the beginning of life, a chiral choice was made. Either by accident, by the accident of the first spontaneous combination of the organic molecules, right? Or some preferential energy difference, which doesn't seem right because parity is conserved. This choice was made. It's a big mystery in origin of life studies. It shows up in our biochemistry in all kinds of ways. Pharmaceuticals, chirality is extremely important in the production of pharmaceuticals. For the over 50 crowd, Prilosec is a chiral molecule. One of the handednesses does the job, right? You have to eat twice as much, right, to get the right dose of one-handedness. Okay. The molecule that gives the flavor of spearmint is the enantiomer of the other molecule that gives the flavor of caraway. Right? Same molecule, two different configurations, your taste buds do something totally different. I think there's an artificial sweetener, which is kind of like a sugar, but it's left-handed. The left-handed thing works okay on your tongue. You get the sweetness, but because it's left-handed, it's indigestible. It's all over in the pharmaceutical industry. Nevertheless, you can't use any of this to get the message to your alien friend because their biochemistry might be totally different. If you want to appeal to something fundamental, you've got to talk about physics. So let's talk about chirality and particle physics. The elementary particles, I was talking about that screw sense, that thread sense. I'm talking about that because we're going to get that out of elementary particles. The elementary particles, you could think of them as billiard balls, are like spinning billiard balls. They have an intrinsic spin. They spin all the time, right? And if you use your right hand to think about the sense of spin here, the fingers do the spinning and the thumb does the pointing. The one on the left there is spin up, and the one on the right is spin down. All right? And the spin comes in quantized units. Particles can have total spin. It's the total amount of angular momentum, a half h bar, 1 h bar. Since we can think of them as up and down like this, sometimes we just draw an arrow to talk about the sense of the spin up or down. Now, we can get a kind of a thread sense, like a screw sense, by combining the spin of the particle with its motion. So if a particle has a momentum p and has its spin vector aligned with its motion, like this one, we call that a right-hand spin. See, if I use my right hand and I point my thumb in the direction the particle is going, my fingers curl around like this spin here, that's a right-handed spin. It's a right-handed thread, okay, that particle. The particle on the bottom has its spin pointing the other way, right? And so if I put my thumb in the direction the particle is going in, and I want my fingers to go in the direction of the spin, I have to use my left hand. So these two cases of a particle spinning along its direction of motion or spinning opposite to its direction of motion are kind of a right and a left. Okay? Righty-tighty, lefty-loosey. Fundamental particles. This property, the helicity, it's chiral. Here's a left-handed particle approaching the mirror. The spin of the particle, in the sense that I've drawn it here, is not reversed by the mirror, but the direction of the particle is. A mirror turns a left-handed particle into a right-handed particle. The same way a mirror turns a left-handed screw into a right-handed screw, okay? So in any physical process where we'd be looking at the helicities of the particles, at the sense of their spin along their direction of motion, if nature respects the mirror symmetry, we expect as many of these as we do of these. Okay? Back to our story about tests of parity conservation. So there was this puzzle in particle physics at the time. There was a fundamental particle that seemed to have both plus and minus parity. How could a particle have both? Two young theoreticians, T.D. Lee and C.N. Yang, checked the literature and noted that there had never been a test of parity conservation for the weak interaction. It was a particle that had a weak decay. What is the weak interaction? Let me remind you, one form of the radioactive decay of nuclei is when a nucleus actually changes its proton-neutron ratio. In this case, carbon with 6 protons turns into nitrogen with 7 protons. That means the charge of the nucleus is increased by +1, and it conserves charge by emitting this negative beta particle. In this example here, this is first, betas is figured out and labeled by Rutherford. So here's the radioactive carbon nucleus turns into a nitrogen nucleus by emitting this beta particle. Now, secretly, we know what's happening inside is one neutron is turning into one proton by giving off an electron and a ghostly partner of the electron called the neutrino. So you see here the charges add up to the charge on this side. Charge is conserved. Charge has been conserved by the ability to create a particle to carry the charge away. Actually, the neutrino is a kind of an antiparticle of the electron. What we see here is our first example of the creation of a particle-antiparticle pair. So Lee and Yang noticed that the mirror symmetry had never been tested for beta decay. And they suggested a way to test it, which is if you got a sample of radioactive nuclei that emit beta particles, like cobalt-60, and use the fact that the nuclear spin gives them a magnetism. The spinning particles are they have a charge, and so it's like a spinning current, and it has a magnetic moment. It becomes like a compass needle. If you put them in a strong magnetic field, you could get them all lined up in the same direction. And then look at the direction in which the beta particles come out. Now, this is a combination of a momentum and a spin. So it's like our helicity variable. It's like a thread. Right? In this example, where the electron travels in this direction with respect to the spin, would be a right-handed decay. If parity is conserved in the weak interaction, we could reflect that in a mirror. In the mirror, right would turn into left. We would expect to see the electron traveling opposite the direction of spin. And if the world is if you can't tell the difference between right and left, that means you ought to observe equal rates of the electron traveling with the spin and opposite the spin. Now, you can't observe the spin But the spin has been set up by aligning the nuclei with a magnetic field. So you would look at the direction of the beta electron with respect to the magnetic field. And you better see the same number going forward and backward with respect to the field. The experiment was performed by a team put together by the great experimental physicist C.S. Wu. And the answer is that the electrons all went backwards. Right? That this beta decay violates parity. The picture of it would be like this. Here was what we expected in a world where you can't tell the difference between right and left. The number of decays with a right-handed thread, with right-handed helicity, would be equal to the number of decays with a left-handed thread. In fact, the right-handed one doesn't exist. This weak interaction is completely left-handed in the sense in which I've described it here. It means the world has a fundamental left-handedness to it, right? So, you know, I talked earlier about somewhere at the beginning of time, life chose all the left-handed amino acids, right? Somewhere at the farther back in the beginning of time, right, when the laws of nature were being chosen, right, when the world was crystallizing out of the Big Bang, right? The weak interaction chose to be left-handed. And therefore, there is a way, a fundamental way in the world to distinguish right and left. So when you get back on the phone with your alien friend, right, you say, here's what you do. Okay, you get your sample of cobalt-60 and a paramagnetic substance and liquid helium and an anthracene crystal, and you make that measurement and look at the way those electrons come out, and then hold your hand up, right? And that one's your left hand. You can do it. The world is left-handed. Put a kind of a capstone on this symmetry business. The mirror reflection is called a discrete symmetry. Discrete in the sense that, you know, you're on the right or you're on the left. It's not a rotational symmetry like all of these positions that I'm rotating through are equivalent. There's only two situations with the mirror. You're on the right or you're on the left. It's a discrete symmetry. Here's another discrete symmetry. Imagine there's a kind of mirror where we could reflect all of the particles into their anti-partner. The antiparticle. What is this antiparticle? Every particle's got one. The antiparticles have the same kind of space-time properties as the particles. Small billiard balls, they have momentum and spin. But every quantum number associated with those particles is the opposite. They have the opposite charge, the opposite baryon number, the opposite lepton number, all kinds of kind of abstruse quantities and extra dimensions and the like, right, are all the opposite. This is what allows us to create and destroy particles. Remember I said in beta decay, right, we created an electron in this neutrino. The neutrino is kind of an antiparticle of the electron. Because you see, when you combine a particle and its antiparticle, the charges add up to nothing. It's a way to take the stuff and get it back to nothing. Well, the energy is still conserved. So when an electron and a positron meet each other and annihilate, the energy goes into a quantum of electromagnetism, the photon, which can then rematerialize as a particle-antiparticle pair. Other kinds of particles, right? So antimatter, you know, it's the way you can make something from nothing. It's the way you can make a universe starting from nothing. Because as long as you make particle-antiparticle pairs, they still sum up to nothing. Of course, the energy's got to come from somewhere. So imagine a discrete symmetry where we just reflected all of the particles into their antiparticles. Turns out the laws of physics remain the same. Here's an example from my favorite book. Here's a charged particle moving between the plates of a parallel plate capacitor, where one plate is charged positive and one plate is charged negative. The positive particle is repelled from here and attracted to here. So its trajectory is like this. Now we reflect this in the mirror of charge conjugation. The negative plate turns into a positive plate. Positive plate turns into a negative plate. The test particle turns into a negative particle. It's repelled by this one and attracted by this one, and you see the same motion. So you can't tell whether you're living in the world or the anti-world. And let's put it another way. We don't know whether we're matter or antimatter. Right? You only know that if you meet your anti-partner, don't touch them. And I was talking about this with my partner Catherine once. Catherine is here. And she said, when you guys talk about this stuff, what do you smoke? And I thought, oh, come on, honey. We're not like that, but we like to enjoy a glass of wine from time to time. Oh, I'm still not ready. Okay. Now, last chapter. Where were we? Back to our story in 2009. An hour west of Chicago, near Naperville, is the Tevatron Collider at Fermilab. So in a separate accelerator here, protons are accelerated, slammed into a target. The collisions produce a small fraction of antiprotons, which are selected in crossed electric and magnetic fields and steered to a small storage ring where we can accumulate the antiprotons, accumulate a beam of antimatter. It's antimatter engineering. And then the antiprotons can be reinjected into the big accelerator in one way or another. And the counter-rotating matter and antimatter collides in two places at the CDF and the D0 experiments. Now, when we go to these high energies, what we're doing effectively is probing smaller distances. There's an inverse relationship between the sort of energy of the collision and the distance scale, the characteristic distance scale that's being explored. You know, so collide at low energies, you could collide atoms, and the atoms bounce off of each other, and you don't get to see what's inside. At very high energies, there'd be enough energy to overcome the Coulomb repulsion of the electrons, and the nuclei could collide. At even higher energies, you'd see the protons and the neutrons in the nuclei colliding. And so what we see as we go to higher energy is, that nature has this, is this kind of an onion. As we go to higher energies, we sort of peel away individual layers, and each layer has its own characteristic set of phenomena for which the sort of energy of the collision is a characteristic energy. The world is this onion. A nested, it's like one of those Russian dolls, a nested set of scales. And at each scale, there's a characteristic set of phenomena. It's kind of like a separate world at each scale. Okay? You know, out here in our world, we have weather. All right? Down inside the proton, no weather. Instead, it's a seething relativistic swirl of quarks exchanging gluons, right? The quantum of the strong force. It's its own world of phenomena, right? Down at that scale. In the Tevatron collisions, of the proton, we're looking at a distance scale which is 1/10,000th the size of the proton. So we're so far inside the proton, you can't even see the edge of the thing, right? And at that scale, we're seeing collisions between the constituent quarks. The proton is actually a kind of an atom made of these smaller particles called quarks. And at these energies, we see the collisions between the quarks. And all kinds of things happen. The collisions occur in the detector at 3 million times a second. All kinds of processes are explored. We run that thing continuously and sift through all that data and pick out the processes that we're interested in. And one that we've been interested in here is where a quark and an antiquark, a U or a D quark and antiquark, collide and annihilate into a quantum of the strong interaction called a gluon, which then rematerializes as a pair of top quarks. A top quark is a quark like the U quark that's way heavier. The U quark is almost massless, and the top quark has the mass of one fundamental particle with the mass of a tungsten nucleus. Okay. And the top quarks then beta decay. This origin of radioactivity, the origin of the sort of decay of the neutron, is really that the quarks inside change their identity through beta decay. So a top quark changes into a bottom quark, emitting a beta particle. Or it changes into a bottom quark, emitting a different kind of quark-antiquark pair. So, I say like we make these particles, but we don't get to see this thing because it's going to decay. And then if there's quarks involved in the decay, they turn into showers of strongly interacting particles. And so we have to observe this thing in the CDF detector, which is two kinds of detector technologies threaded by the beam pipe. On the outside, absorbers that measure the energy flow, and on the inside, imaging detectors, kind of like electronic bubble chambers that allow us to see the trajectories. And a top-anti-top pair in the detector looks like this. There's nothing on it that says it's top. We have to figure out ways to go into this sea of particles and discern that this particle here is an electron, and this particle, this jet, this spray of particles here is originating in a B quark, and that could have been this electron and B quark. And this situation on the other side would give us 3 sprays of particles, and you see here 1, 2, 3 on the other side. So, getting down to the level of calling it a top quark is an inference based on an experimental observation in a complex device. You need a lot of talented people to put a thing like this together. This is our team at Michigan. Research scientist Monica Tecchio, postdocs Tom Wright and Alexei Varganov. Alexei came all the way here from the Russian high-energy physics laboratory at Novosibirsk. 3 industrious graduate students. My collaborator of way too many years, Myron Campbell. And this slide was from a recent program review. Just to say a little bit about the people. You can see all the jobs that everybody does. We don't spend too much time actually sitting around thinking about reflecting the world in mirrors. We've all got jobs to do to pull this off, and the stuff that I'm showing you here is due to the talented work of these people and our 500 collaborators. Right? The CDF collaboration is an international collaboration of 50 laboratories and universities, 500 people, all dedicated to the pursuit of this physics. And what might be happening in the production of top quarks? Now, this is what we know happens. Quarks and antiquarks annihilate. Top and antitop are produced. Now, what if, at the energy scale of our collisions, we were turning on a new interaction? a new exchange particle here that's massive. We don't see this interaction in our world because our world is at low energy. But if we get up to these high energies, we could kind of excite this additional mode that would be spin 1 like the gluon, but left-handed. What would happen if there was a left-handed interaction? Well, the quarks and the antiquarks would have to participate in the left-handed way, which would mean the quark would have a left-handed helicity, and the antiquark would have a right-handed helicity. So the projection of their spins along the direction of motion would be like this. The quarks are spin a half. This is the situation that we get if the new interaction is left-handed. Now, in the collision, the angular momentum of the quarks combines, the spin angular momentum combines into the angular momentum of the exchange particle. So this thing is a big spin 1 pointing to the left. And then when the top quarks come out, they have to respect the left-handed thing, right? So this one has to have, the top quark has to have a left-handed thread, and the anti-top quark has to have a right-handed thread. And the way I draw it here, it works out just fine, as long as the top quark is going to the right. That is, as long as the top quark is going forward. See, if the top quark was going to the left, the anti-top quark was going to the right, and I tried to preserve this chiral sense of leftness, then the spins of these guys are pointing the wrong way to add up to this. So I can't preserve my left-handed hypothesis and angular momentum. This one does not work. So if there was a new interaction like that, the top quark has to go forward. So now you can understand why I stare at this picture a lot. This picture shows the distribution of top quarks in this kind of forward-backward coordinate system compared to the symmetric theory. And you see there's a kind of a preference for the top quarks to go forward. Well, you know, experimental physics can be very thrilling, right? But it can also be really vexing. This number up here in the corner, 9.8 plus or minus 3.6, that's the asymmetry parameter of the data. The third line here is the asymmetry parameter that we expect. We expect 0. And the asymmetry in the parameter in the data is 9.8 plus or minus 3.6. So if you compare the observation to the uncertainty, it's 2.7. The excess, the positive excess, is 2.7 times the error. Now, this is comparing the measurement to its error it's a well-known procedure in making measurements. You know, if the measurement was smaller than the error, I would say, you can't, ignore it. Your error is bigger than what you're trying to measure. Here, the measurement is a little bit larger than the error, but not much. And the science of doing this comparison, the statistics of this is well understood. Random errors, random fluctuations in the data that we observe, right, would produce a 2.7 sigma fluctuation 1 out of every 330 times. So that's not enough to conclude anything. As the number of events increases, as the statistics increases, the statistical precision of this will increase, and we'll see. But this is, to me, this thing has all the majesty and frustration of experimental physics in it. It's kind of like romance. You meet a measurement that's really fascinating. but you don't know how it's going to work out at the end. But it's so fascinating, you just keep going. All right, well, from the ridiculous to the sublime, and I'll be done. I want to remind you that the last time processes of these energies occurred naturally was when the universe was very hot and everything was at high energy. And we can map the succession of distance and energy scales onto the time and temperature scales measured from the Big Bang. So here's, here's the atomic physics scale at a temperature of 3,000 degrees, 30,000 years after the Big Bang. And earlier than that, it was too hot for the atoms to coalesce, but the nuclei could coalesce 3 minutes after the Big Bang. And so here's these, and earlier than that, the nuclei couldn't coalesce, but the protons and neutrons would be bouncing off of each other. And so here's this onion again, the succession of scales, showing that the succession of distance and energy scales are each showing us what a different epoch was like in the development of the universe from the Big Bang. And so every point in space, if you look down through the microscope, through the succession of scales, you're looking actually at a history of the epochs since the Big Bang. The characteristic scale that we explore at the Tevatron right now is here at, I can't see this very well, 10 to the minus 10 seconds. And if we happen to be seeing something new in the interactions of top quarks, it's telling us that, the reason the top quark is there and the reason there might be a new interaction there is it's part of the picture that explains why the Big Bang happened, why there is something instead of nothing. And that's why we do this with the generous support of you taxpayers. Right? And thank you very much.
Saturday Morning Physics is sponsored by the Amidei Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.